Raise your hand only. Only thing that you want to raise your hand, no cross answer. Whenever I will ask to anybody, please reply. Tell. Group 7. Okay, correct. Group 17. Okay, sit down. So in group 17, which is the first element? Which is the first element in group 17? First element you have to speak. Raise your hand. Only thing is that you have to raise your hand. Not that. Okay, tell. Chlorine. Good. It is chlorine. So now you tell, now just you see your children. So now you see. Suppose I am writing now H2, O2, N2, one set. Then another set I am writing. let it be H2O, NO2, or let it be HN. So these two sets. So this is one set. This is one set. This is second set. Are you getting? Okay. What is the similarity in first set? Raise your hand. What is the similarity in first set? Raise your hand. What is the similarity in first set? Okay, tell. Similar atoms. Very good. So similar atoms bonded together. Similar atoms. And what is the similarity in second set? This side. Raise your hand. Yes. Different atoms bonded together. Okay. Now in first set, just now we have seen that in first set similar atoms bonded together. In second set different atoms bonded together. So there is a name particularly to this one, and there is also a name particular to the second set. So what do we call it? That means whenever similar atoms bonded together, what do we call? And whenever different atoms bonded together, what do we call it? Okay, anybody? Very good. It is homonuclear, and second one is
Heteronuclear.
It is heteronuclear. Very good. So this is homonuclear molecules. So this is homonuclear molecules, and this is heteronuclear molecules. Okay. And you see, just now told you that in periodic table, group 17. Okay. Group 17 that is called halogens, and here also halogen is second set. In one of the molecule there is one halogen. It is bonded to some atoms. Can you identify second set which molecule halogen is bonded? Just raise your you have to raise your hand. Yes. Yes, very good. It is HN. Now you see, dear children, all of you see. So this is one periodic table. This is 3D. Sit down, sit down. So this is one 3D periodic table. Just you see this one. So here it is very clearly. Just you see this is a 3D model of the periodic table. So it is group 17. It is clearly mentioned here. So group 17. So it is the right hand side and P block elements. Is that it? So this is the 3D shape of the periodic table. Okay. So now you see another thing. Just continue to this one. So now in there is one concept that is called electronegativity. Electronegativity. So already we know regarding this electronegativity concept. Tendency of an atom to attract the pair of electrons towards itself. Okay. Now you tell me, just to consider the first set in homonuclear. After that you will consider the second set heteronuclear. In first set, is there any electronegativity difference? Just you raise your hand and tell me. No cross answer. Because now we are now in the prime focus of your first and second set. In first set, any electronegativity difference exists in first set? Tell, any electronegativity difference are okay. Out of these two sets, where you are marking the electronegativity difference? Anybody? First or second? It is second. Absolutely correct. So it is second set. So we can easily observe the electronegativity difference because of heteronuclear nature. So definitely because of dissimilar atoms, and we know that different elements have different electronegativity. Okay, so definitely some electronegativity difference you will find here. So that's why, since it is heteronuclear, some electronegativity difference you will observe, and in first case no electronegativity difference you will find because it is homonuclear molecules. And due to this electronegativity difference, in second case you will observe the polarity. You will observe the polarity, or that is called charge separation, charge difference you will find. But no polarity you will find in first case because the electronegativity difference is 0. since the electronegativity difference is 0, so we will not find any kinds of polarity in first case. Is it clear to everybody?
Yes,
so in
sir.
second case, some polarity we will observe and see. So just coming to this side, this electronegativity difference leads to polarity. That means that these are the polar covalent bonded molecules. So second one, this is the polar covalently bonded molecules. So you can write polar covalent bond, and definitely second set, since it is polar covalent bond. So what should we call the first set? It is definitely the non-polar covalent bonds because of this electronegativity difference is 0. So we are not getting any kinds of polarity in case of your first set. So non-polar covalent bonds. Okay, isn't it? Now you see here. So it is clearly represented here in this slide. So you see, so it is the difference. Your polar. This is clearly indicated. Non-polar covalent bond. Here it is clearly indicated. H2O2 and Cl2. So definitely it is a similar kind of atoms. So definitely it is the non-polar covalent bond. Because same kind of atoms bonded. So no poles you get. Pole means charge separation. The polarity means electronegativity difference. Okay, and this can be represented as, suppose we are writing HF, so we will represent like this. That is arrowhead moving towards the fluorine because of more electronegativity. Since fluorine is more electronegative than hydrogen, so this is represented, and this is the representation on this exactly polarity. One term is coming, that is your dipole moment, and this dipole moment is nothing but it is the multiplication of charge into distance. And this can be represented as symbol mu. Okay, this is the symbol of dipole moment, and this is equal to your C into D, and here C means charge into distance. Okay, charge into distance. So here C stands for, here C means the charge and the distance. So distance between the two poles, and here the charges are there. Electronegativity difference is there, and the unit. The unit for this dipole moment is dBi. So this is your dBi represented as capital D. It is dBi. Okay. Now coming to next, just you see. So here very clearly written. So when your polar bond is represented here, in case of polar covalent bond, axial charge separation is there. And here it is explained. Okay. So here we have explained now. So you can see. Just now, here we have just written like this. HF. Just you see here I am writing HF. Here it is very clearly written HF. And next I am writing HCl. HCl I am writing. Okay. And this can be represented as like see. This is the dipole moment symbol, arrow mark. So arrowhead pointing towards your more electronegative atom because of more electronegativity of fluorine as compared to your hydrogen. And second case also same thing, because halogen there we all know electronegativity increases across the period. Just now told to you, so since it is the periodic table, you see this is the 3D representation of periodic table. Like this, P block right hand side, S block you left hand side, D block middle, and A block at the bottom. So electronegativity increases like this. So and group 17, since period increases, so definitely your group 17 possesses high electronegativity. So that's why here it is the electronegativity difference. And here also same thing we are writing now. And there is very similar way. You see this one. And okay. Now the most important thing is written here at the down of the slide. You please mark here greater the difference in electronegativity of bonding atoms, more will be the polarity. This is very important one. This one is very important one. And you see, we all know that in periodic table, group 17, first element fluorine. And we all know that fluorine is 4.0, maximum electronegativity of fluorine. It's the highest electronegativity element. Isn't it? Are you getting my point, my dear children?
Yes.
Fluorine is the highly electronegative element. The value is, it is 4.0. Okay, we have already seen it. Okay, now where we have seen it? That is periodic table we have seen. Now you see that one represented here. So HF is greater than HCl, greater than HBl. So what does it mean? It is written in which order? It is in increasing order or decreasing order? Raise your hand. It is decreasing order. Decreasing order means greater the difference in electronegativity, more in the polarity. So ultimately HF possess high dipole moment or highest polarity. Now you getting my point? Because of this scoring, your highly electronegative element. Now this coming to the next now we will continue. Now here you see this dipole moment. Dipole moment, you see arrow head and tail, this plus, okay. And this dipole moment is absolutely one vector quantity. Already we know that is scalar and vector. We know. Anybody? What is the main major difference between one scalar and vector? Anybody raise your hand? What is the basic difference? Okay. Out of this scalar and vector, where direction is normally we find direction properly.
Yes,
It is vector. Very good. So now just now it is given very clearly. It is represented arrow mark. So it is a vector quantity. It is the vector direction. Okay. And vector. So dipole moment just now we have seen it is a vector quantity. So if it is vector, so definitely there must be vector addition, because if a molecule is heteronuclear, definitely vector addition will be there, and there must be resultant vector. Just like we have seen. Suppose this is a case, this is a case, this is the two arrow. Okay, we have seen it in physics and math also. So this will be the resultant vector, isn't it? Resultant vector addition. Now few cases I am showing here. Few cases I am showing. Suppose I am writing now vector addition. I am showing to you. First you try to understand the vector addition. Suppose this is now moving in this. That means your arrow head pointing towards more electronegative atom, and tail that is less electronegative atom. So now if I am writing this is the first case. Now I am writing this is the another case. Just you see properly. You see. This is the first case, this is the second case, okay. Now you tell me, my dear children, out of these two cases, where you will find zero dipole moment?
Second.
Very good, absolutely correct, because they are in opposite, reverse directions, okay. And by vector addition, definitely zero dipole moment, you will find it second, and definitely some resultant, your dipole moment you will find in first case, because in same direction. This is exactly similar to this also, yes or no? Now this case and this case, they remain same, because in both the directions. So you will definitely find, this case possess definitely certain kinds of dipole moment. Okay. Now this one also we will discuss now. Okay. So now next one, next slide you show. Next slide you Okay, next slide you see. Next slide you see. This is very important slide. This one also already just now here it is explained. Now here just this is the application part. Now we will apply this situation in different circumstances or in different situations. In front of you, these are the different molecules presented here. So now you see, just you see my dear. This is which molecule? Which molecule this one is represented? It is H2O. Fine, it's fine. Okay, it is H2O. So now you see arrow mark pointing towards oxygen. Why? Oxygen is more electronegative than hydrogen. So which one? We have to see that what is the major setback here. That the element, the atom which is more electronegative, towards that side, your head must be pointed towards that side. Okay? So it is now you see this side oxygen, this is also oxygen. Towards. So now for this two, this is the resultant vector. Yes or no? So now you coming to this one, PEF2. So PEF2 you see, PEF2, BEF2 just a linear shape. Just you see now. This is two pencils now. Just suppose this is beryllium atom. So I am showing this one. This one you see, just linear shape, completely linear shape. This one. This is completely linear shape. Suppose this is the what? This one is oxygen. This one is oxygen, and this is hydrogen. What is B? Oxygen, and this one is bent. This is your water. This one I am doing.
Yes.
This one I will say bent. This is bent now. This is bent. But now by increasing the bond angle, like this, 180 degree. Linear means 180 degree. Just now I am showing this one. Just you see this one. Okay. Now this two model now it is clear all of you. Like this. This is one. So this model is for this one, and for this just I am doing like this. Just like this. So this is linear. Okay. This is 180 degree. Isn't it? And this is 104.5 degree. Exact bond angle. Already we have seen in valence cell electron pair repulsion theory. We have seen that ESCTM theory. 104.5 degree. And for linear shape it is 180 degree. So see now this one it is 104.5 and this is 180. Why? Because this is linear. Understand? Now you see In this case, now we compare this dipole moment with the molecule and this resultant dipole moment. Now, can you tell me? Can you guess? Raise your hand. In which one? In which case your dipole moment there will be cancelled out, means zero dipole moment. Very good. It is correct. It is B. Now, getting my point, all of you?
Yes.
First case is very clear. Okay. Now coming to second situation. It is another interesting case. It is another interesting case. So this is trigonal planar set. This is trigonal planar set. It is 120 degree. Now you see this design I am showing to you. Just you see like this. Just see now. Just like this. Trigonal planar set. Isn't it? This is very similar to. This is very similar to or you move like this, triangular planar. Just to move like this, isn't it? Just to move like this. It is BF3 or BCl3, same thing. BF3 or BCl3, same thing, same situation. It is, what is the bond angle? It is 120 degree. It is AB3 type molecules. It is just like AB3 type molecules, but one thing is missing here. One thing is missing here. Can you guess that one? Here, no doubt in every molecule bond pair is present. But now you tell me, bond pair is present in this molecule or not? 100% it is there, because if there is no bond pair, molecule do not exist. Molecule never exists without bond pair. Bond pair is the fundamental criteria, the most dominant criteria. But another thing is that lone pair, may or may not. Now you guess, my dear children, here lone pair is present or absent. Raise your hands. Tell. How? You have to explain that. If you are saying that means by thinking you are saying. Now explain me how. Okay, in boron, just you clarify what is the electronic configuration for boron. Tell me. What is the electronic configuration for boron? Very good. 1:2. 1:2. Then 2p1, because its atomic number is 5. So sit down. Okay, now you got the point, I think. 1:2, 2:2, 2p1. So in outer cell it is 3. Outer cell it is 2:2, 2p1 is the outer cell. So it is 3 electrons, isn't it? It is 3 electrons. So 3 electrons will be involved in bonding. And 3 electrons now it is already involved in 3 covalent bond. Yes or no? Just you see this one. Just you see the ball and stick model, or you see this one. Just you see this one. This is the ball and stick model. You see, ball and stick model. This is the ball and stick model. It is very prominent now. Now you getting my point? It is B. It is F, F, F. Now you see, okay. So this is the boron, and 3 electrons. 1 electron here is involved with hydrogen, and another electron here involved in bonding with hydrogen. This one involved. Now all the electrons used up, or any electron left in boron? All the electrons are used up. So there is no chance of lone pair. What we can say, this is the electron deficient molecule, isn't it? It is electron deficient, and this is one of the limitations of octet. Already we have seen the Lewis-Strauss structure. BF3 and BCl3, octet rule is not satisfied. Here octet central atom, normally it is satisfied, but in this case it is the exceptional one, it is deviated. Now can you tell me, my dear children, octet rule is restricted up to which period in periodic table? You have to raise your hand. Yes. Very good, absolutely correct. It is applicable up to second period. It is definitely. Sit down. Very good. Okay. Here it is clearly written, dipole moment formula is clearly written here, charge into distance. Is it okay? Yes. Charge into distance, and the unit is very clearly mentioned here, dBi. Already we have written here dBi. Already we have seen. Already I have written it here. That is dBi. And 1 dBi. This is the value. 3.33 multiplied 10 to minus 30 Coulomb into meter. This is Coulomb into meter. And coming to next one, now you see here, it is a very interesting one in this slide. You will see now the 3D model in 2 varieties. In 2 varieties means, in one case you will see with bonding 3D model, and at the side by side you will notice the space filling model of that molecule itself. So let us see it. Okay, so let us see how it is represented. So now you see, it is a very interesting one. Now you see, so this is the 3D structures of some molecules, and here you see, this is the SF6. SF6 it is represented in bonding form. Yes or no? This is represented in bonding, not without. So there are 6 bonds. So now you see, this is the space filling model of that molecule itself, that SF6. So this is the SF6. Now you see, this is the CH4. In CH4, it is 4 bonds, it is with bonding, it is represented. Now you see, this is the space filling model of that molecule itself, that is CH4. Okay, so for a molecule, 2 types we are represented. Here it is NF3, NS3 in bonding pattern, and it is 3D. Mind your children, this is 3D. This is 3D representation, and this also we can show the space filling. This is the space filling for NF3, and this is the space filling for NS3. So this is this is all about your 3D representations, and in 2 states we have seen molecules, particularly in bonding state as well as in your what you call it, space filling state. Thank you everybody. Thank you. Thank you.